In the last video, we started looking at the hyperfine interaction, which was essentially a magnetic field interaction between the nuclear spin and the electron spin in the hydrogen atom. So basically, if you a simple sort of classical model of this is if you think about the nuclear spin as being a dipole moment, it's going to have magnetic field lines that go like this. And if you think of the electron as well as being, a magnetic dipole moment, it's going to have its magnetic field lines. And the magnetic field produced by one is going to interact with the dipole moment of the other. And if we look at just classically the energy of that interaction between the magnetic field and the dipole moment, you have it's equal to the dot product of the magnetic moment of the one with the magnetic field produced by the other. So we started with that sort of picture of these two, of the electron and the proton that make up hydrogen, and we ended up looking at what we call the hyperfine interaction, this interaction between the electron and the nuclear magnetic moment and the electron's magnetic moments. And what we ended up arriving at is that the Hamiltonian for that hyperfine interaction, which is going to perturb, we've treated some internal perturbation to our hydrogen atom, is equal to, the simplest way we wrote it was A over h bar squared S dotted with I, where A was just some constant that came out of everything after we did some calculations that was equal to 2 pi over A naught, 3 pi over A naught cubed, the G factor of the electron times the Bohr magneton, G factor of the nucleus of the proton, times mu, not B, of the nucleus. And S was the spin operator for the electron spin operator, and I was the nuclear spin operator. And this is the contact term. There were other terms in the hyperfine interaction that had to do with the orbital magnetic moments and of the electron, and basically when the spins were far apart from each other. But the one we were most concerned with was this hyperfine interaction. We were looking specifically at L equals 0 state, so the orbital angular momentum of the electron was 0. And this is what we got. This was called the contact hyperfine term. Contact because it essentially arises from when the electron and the proton that make up hydrogen are in contact with each other. That the wave function of the electron being overlapping with that of the proton. What we're going to do today is we're going to look at this in more detail. We're going to start to think of how can we look at this Hamiltonian and see how it affects the energy levels in our hydrogen atom. But to do that, we're going to have to sort of recap some things about angular momentum. Both of these operators in this Hamiltonian are spin operators that affect the intrinsic spins of these things. So we're going to do a bit of sort of a review and a general, discuss sort of the general way we can look at angular momentum. Recall, rather than focus on like the difference between the nuclear spin and the electron spin operators and that, let's just think about general momentum operators, right? So if you think back to our hydrogen atom, we had two types of angular momentum. Spin angular momentum, right? And that was sort of, the things we thought about with that, or the operators, were the sort of magnitude squared of the spin operator, of that spin angular momentum. And it had quantum numbers associated with it, just the angular momentum quantum number and the magnetic quantum number, the spin quantum number. And that S squared operator had eigenvalues S plus 1, h bar squared, S, ms. That had that eigenvalue equation. And we also had the Z component of the spin angular momentum quantum, the operator, and that had the eigenvalue equation that looked like this, right? with eigenvalue magnetic quantum number times h bar and that. So for our spin 1/2 system, this ended up being, you know, s squared operating on the 1/2 or the spin up state was ended up equal to 3 over 4 h bar squared 1/2 1/2, and the sz operator acting on that same 1/2 state ended up just being h bar squared over 2 1/2 1/2, and this could be plus or minus the two different eigenvalues for that. This spin angular momentum was an intrinsic property of the electrons and particles we were looking at. The other type of, when we got to the hydrogen atom, we also looked at orbital angular momentum. And it similarly, it had quantum numbers, an orbital angular momentum quantum number and an orbital magnetic quantum number. And it had, we looked at two operators in general with it, the L squared operator, which operating on that had an eigenvalue equation of L plus 1, h bar squared, L ml. And the z component of that orbital angular momentum had a quantum, or an eigenvalue equation that looked like this, right? And you can quickly see there are some similarities to this. This orbital angular momentum arised from sort of the orbital motion. It depended on which eigenstate that electron in the hydrogen atom was in, and its orbital motion gave it some orbital angular momentum that we associated with that. The spin one was intrinsic to the electron, so they both, these angular momentums arose from very different things, but there are some similarities in how we dealt with them, right? When we're not really concerned with the origins and just the resulting angular momentum, we ended up having these very analogous sort of angular momentum operators with angular momentum with the same sort of eigenvalue equations. And in general, when that's the case, and we're just looking at generalized angular momentum, we can, we'll call that, instead of L or S, we'll just call that generalized angular momentum J, and it'll have an generalized angular momentum quantum number and a generalized magnetic quantum number associated with it. There are generalized, J squared operators that have the same sort of form of eigenvalue equations that the other two types of angular momentum we looked at had. A z component one and that has these types of eigenvalue equations. Right. And another thing we noticed when going through these, or hopefully we noticed, is or that we realized, is that for a given set of S and MS or L and ML quantum numbers, for a given L or a given S, for a given angular momentum quantum number, the magnetic quantum numbers could take values from negative, in this case L, to an integer steps all the way up through positive L, right? So in general, with the total, if we look back to our spin case, S is equal to 1/2, right? So the MS value could go from negative S, 1/2, and then an integer step all the way up to positive S, which just gave us those two possible values, 1/2 and negative 1/2. For orbital angular momentum, your L could be, different values would be 1, and then you'd have negative 1, 0, 1, and so on. In general, we have, for a given J or a given angular momentum, you're going to have a manifold, what we call a manifold of states that go from negative J in integer steps all the way up to the positive J value, right? And these are sort of common things that we noticed, and we're going to build on this and just start discussing how can we look at general angular momentum and how can they combine when we look at systems like this where there are two types of angular momentum, one for the nuclear spin, one for the electron spin in the same system we have to worry about. Other things we had for these angular momentum operators is they had similar commutation relations, right? The x component of the angular momentum, the y component of our angular momentum had the commutation relationship that looked like that. And we also had cyclic permutations of the commutation relationship. So we had these three commutation relationships for the different components, not z, for the different components of our angular momentum, I, h bar, j, y. And we had the fact that all of the components commute with the j squared operator. So j squared jy equals j squared jz. All of those commute, so those commutators be 0. Yeah, like we mentioned before, we have a known sort of basis for these operators where we can define a set of basis vectors that are defined on the j, the angular momentum quantum numbers and the magnetic sort of moment quantum numbers. And we also looked at writing these things in matrix representation. For our spin, for j equals 1/2, our spin 1/2 state, we had the j squared operator, was 3h bar squared over 4, and it was just times the identity matrix. The jz operator in that had h bar over 2, 1, 0, 0, negative 1. As if j, similarly, if you think way back to the S spin 1 system, we had similarly, j squared could be written as 2h bar squared times that identity operator, and the z component in that was h bar 1, 0, 0, 0, 0. And we looked at a lot of things like this, but basically, recapping what we did, the angular momentums we've looked at had eigenvalue equations for angular momentum operators that looked like this. They had commutation relationships like this. In general, we've looked at the sort of matrix representations for different types of these angular momentum systems. So all of this should be pretty familiar. What I want to do now is, or what I'm going to do now is I'm going to define two new operators, a j plus operator that is equal to jx plus I jy, and a j minus operator that is jx minus I jy. And these two operators are going to be analogous to the ladder operators that we had when we were studying the harmonic oscillator, those raising and lowering operators. Ultimately, what we're going to show is that these will serve the same sort of purpose here, right? To show all this, though, we're going to need to know and be interested in what the commutation relations with our other operators are with this operator. So real quick, looking at the commutation relation between the z component operator and the j plus operator, this, of course, by definition is just jx plus I jy. Just those two operators operating in a different order. So it looks like this. We expand that all out. We get jz, jx plus I, jz, jy, minus jx, jz, minus I, jy, jz. And if we look at this, right, you can see that this term minus this term is just our commutation relationship between jz and jx, which we know. And if we look at this term and this term, it's equal to plus I commutation relationship of jz and jy. Or if we want to switch the order of those two, because that's typically how we wrote it above, jz, jx minus I, jy, jz. right? So these are this commutation relationship relates to those, and we know what those commutation relationships are, right? If you think back to up here when we were discussing this, we have Jx, Jy is related to the Jz operator and cyclic permutation. So this Jz, Jx operator is just I h bar Jy. This minus I, this commutation relationship is simply I h bar Jx. If we then just multiply that stuff out, we have I h bar Jy. This negative negative with the i's there becomes plus h bar Jx. Plus h bar Jx. So if we factor out a h bar, we end up with Jx plus I Jy. And this is simply, that's what we defined our J plus operator as, right? So this ends up being, this commutation relation is just h bar J plus. And if we do the same thing with the J minus operator, we get a similar relationship. So we can show Jz, J plus, that commutation relationship is just h bar J plus, and similarly Jz, J minus is equal to just negative, in this case, h bar J minus. So we have those two commutation relations. If we look at them commuting with themselves, I'm not going to derive all of these here, maybe I'll ask them on a homework, but these two commuting with each other gives us just 2 h bar J z. And like, we pretty much everything, the J squared operator commutes with both of those, so that equals 0. Excuse me, which is, is kind of obvious. The J squared operator commutes with both of these, the Jx and the Jy operator. So if we do this sort of thing with the J squared operator, they're all going, all of these terms would end up being 0. Anyway, so we have the commutation relationships for these sort of newly defined raising and lowering or angular momentum ladder operators. And we can actually use these to sort of develop eigenvalue equations for those operators. How do we do that? Let's look at this commutation relationship we just derived, right? We have the Jz operator with the J plus operator is going to be equal to h bar times the J plus operator, right? So if we take those, that Jz, J plus minus J plus Jz, and operate that on one of our eigenstates, Jmj, we should get the same thing that we got if we just operated that J plus operator on that same eigenstate, right? And so if we do that, and just in gory detail here, acting on that would look like this. Jmj has to be equal to h bar J plus Jmj. Right? We know, if we look at this, we know how Jz, the action of Jz on that eigenstate. So Jz, this can be written this way, Mj minus J plus times, this is going to be Mj h bar, acting on that Jmj because that's the eigenvalue equation for that operator, and this is h bar J plus Jmj, right? Now, this is just a scalar now, so we can move it to the other side. And again, I'm going into a lot of detail here that might be obvious to some of you, but let's just do it anyway. J plus Jmj is equal to h bar J plus Jmj. If we bring this term over to the other side, we get jz operating on whatever j plus times jmj equals is equal to h bar j plus jmj plus mj h bar jmj, right? And we can. Oops, sorry, forgot a very important term here. Oops. Sorry, stylus not really cooperating there. J plus acting on J and J. So factoring that out, we have H bar times 1 plus mj operating on whatever j plus jmj gives us, right? So what we see is this is actually an eigenvalue equation, right? We have jz operating on whatever that ket is, gives us this eigenvalue operating on or multiplied by that same ket. That's an eigenvalue equation. So we know that the j plus the action of j plus on one of our eigenstates produces another eigenstate of the jz operator, right? And we know that it's actually we know the eigenvalue of it. The eigenvalue of that jz operating on this is just h bar mj plus 1, which is the eigenvalue, the one up in the manifold defined by that given j, right? So we can see that the j plus operator produces an eigenvector of the jz operator. Sorry, let me rephrase that. The j plus, or this angular momentum raising operator, acting on one of our angular momentum eigenstate vectors, results in the angular momentum operator one higher or one above that the one it was operating on in that manifold. Similarly, if we do this same sort of thing but with the j minus operator and the commutation relationship, we see that the j minus operator brings us down 1. So this is going to be the lowering, and we just sort of showed the j plus is the raising operator. In the same sort of way that the the harmonic oscillator ladder operators work. So recall, we come up here, and for a given value, for a given j value, or a given angular momentum value, we define this ladder or this manifold of mj states, right? So for, say, for the j equals 1 state, that spin 1 system, we had the 1, the 0 h bar, the 1 h bar, and the negative 1 h bar angular momentum states. If we operate j plus, we go up and raise that ladder operator, and if we do j minus, we're going to come down those states in that manifold. And much like we did with the harmonic oscillator ladder operators, we can sort of determine our whole spectrum of angular momentum states in general using these operators. The only piece that's sort of missing to do this is the sort of normalization factor. Or what we've shown here is that this j plus operator produces a ket that's proportional to the state 1 higher in that manifold, but it doesn't necessarily preserve normalization and all that. So what we need to do, so what we've shown is these raising and lowering operators acting on j and mj give us some vector that's proportional to j, mj plus or minus 1, but not necessarily normalized. So there's some factor out front that makes this normalized. So we need to sort of go through this to determine what the action of these operators are on this. And to do that, we just normalize these and see what that C plus is, right? So we know normalization is essentially just that, right? So if we take these two, this equation here, and normalize them, what do we get? Well, we have J mj with J plus minus that, J plus minus JMJ is going to be equal to JMJ plus or minus 1, C plus or minus complex conjugate, C plus minus JMJ plus or minus 1. On this right-hand side, this is just C plus or minus squared. So we can determine what that is by looking at what the result of this thing is. And if we go through that, well, let's just plug in what our definitions for that were, right? We have J, MJ, and the J plus or minus operator is just JX minus plus, because we're looking at the complex conjugate of IJY. And then on this side, JX plus or minus IJY times JMJ. Going through all this, this ends up being JMJ, again, JX squared plus JY squared minus plus JY JX plus minus JX JY, all acting on JMJ. If we look at those last two terms here, this and this, we realize this is essentially just a commutation relationship between JY and JX. So this is equal to JX squared plus JY squared, minus plus the commutation, or plus minus commutation relationship between, just sloppy here, sorry. This ends up being plus or minus I times the commutation relationship of JX, JY. So we'll just do that, JX, JY, acting on JMJ. This whole thing, again, is JX squared plus JY squared minus plus, because of that I H bar, the commutation relationship being equal to I H bar JZ. This is just minus H bar JZ acting on JMJ. Now, we know how JZ acts on these eigenstates. We can rewrite JX, JY. We know that J squared is just JX squared plus JY squared plus Z squared. So this JX plus JY is just JMJ. It's just going to be J squared minus J Z squared minus plus H bar JZ acting on JMJ. And now we've written this whole side of our equation here in terms of operators that we know the eigenvalues or the action on these kets, right? So if we just take those operators and operate on the JMJ, this term just gives us H bar squared J plus 1, right? This is minus MJ H bar squared, though, squared, minus plus H bar times MJ H bar, right? So just write that as H bar squared. All acting on JMJ. Simplifying this and just factoring things out, this whole thing ends up being J mj, and that term in the middle ends up being j plus 1 h bar squared minus mj h bar squared. Sorry. Let me write that in a more clear way here. Minus h bar squared, and then we'll just factor out the mj times mj minus plus 1 acting on jmj, right? Or, since these are orthogonal in that, we have h bar squared, factor out that h bar squared, we have j plus 1 minus mj minus plus 1, like that. And we know that this whole thing is going to be equal to this proportionality factor thing we had here. So ultimately, what we've shown is that c plus minus thing is equal to h bar times the square root of j plus 1 minus mj j plus or minus 1. And that gives us that j plus or minus operating on j mj is equal to h bar square root j plus 1 minus mj plus or minus 1 on j mj plus or minus 1, right? And that's how those ladder operators operate on our eigenstates or our basis states in this JMJ basis. And this is what, this is going to be really useful to us. This is where we're going to stop for today, really. Again, just recapping what we've really just done is look at angular momentum sort of in general, not caring whether it's spin or orbital or nuclear spin or electron spin, but just those, in general, angular momentum operators have these sort of eigenvalue equations, and for a given angular momentum quantum number, it defines sort of a manifold of magnetic quantum numbers. The operators have these standard sort of commutation relations, and we've defined ladder operators for the angular momentum that, looking at the commutation relationships of those, we have shown that their action on these eigenvalues or eigenstates are essentially have the effect of raising or lowering the state in that manifold of that MJ manifold for a given angular momentum, and has those eigenvalues. Well, now that we have this and we have these sort of tools or in our kit, we can look at using them to diagonalize that hyperfine perturbation that motivated this whole thing, that interaction between the electron and the nuclear spins, nuclear magnetic moments. We're going to now use this sort of generalized angular momentum to look at that perturbation, and it's, for given L for given L values in that, we'll have degenerate states, and we'll have to diagonalize that Hamiltonian to figure out how that perturbation affects our states. If you have questions, bring them up in the synchronous sessions or email me, and I will see you then.